Okay, this time we're going to see how we can formulate stiffness using the equilibrium of joints, but this is something that we're not going to be using really often. This is something that is possible, so I thought we're going to take a look at that. Okay, alright, so here is the equation that we have seen previously, the truss that we have seen previously. This time, this diagram right here is actually showing the direction of the forces, meaning the forces that were applied to it, also along with the forces that are the support reactions. And the rightwards figure is the same figure as we have seen before. Okay, so the concept here is to use the member forces determining equation. Remember this equation that we had used to determine the member forces after we had figured out the displacements, right? So this is the equation that is going to play the major role here to give us the same stiffness metrics or the stiffness results that we would have gotten using the stiffness matrix method. Okay, all right, so here let me just do one equation here, explain one equation, and the rest of the equations are similar. So right over here we have the force in x direction at joint A. So this is our joint A, so at joint A, and it is supposed to be 0. This is going to be 0, as we know from the equilibrium equations. They're supposed to always stay at 0. So this is supposed to be 0, so we're going to consider all of the x direction forces here. If we consider the x direction forces here, you can see that the xa is present. So we have taken xa. Right after that, the member forces. The member forces meaning there are two members here. One is the AB member, it's going to have a force in this direction, and we also have the AD member, which is going to have a force in this direction. So the directions are being assumed by us. There we go. So since both are in positive directions, so PAB, it has 0 degrees. There's 0 degrees, so there are no degrees attached to it. But on the other hand, we have the AD member, which is a 45 degree member, and we can easily figure out the degree here because the dimension of the truss is being given here. Okay, so right over here we have PAD, and since this is along the inclined angle of 45 degrees, this is going to be cos theta or cos 45 degrees, so plus PAD cos 45 degrees is equals to 0. Now this is where the equation comes into action. Okay, so we're going to change the PAB and the PAD with the equation, this equation. Okay, alright, since AB member is in 0, the theta value for the AB member is 0, then sine theta is 0. That means that this portion is not going to be there for PAB. So here we have the EA by L, which is 500. Right after that we have UB minus UA, which is U3 minus U1. Here we go, we have U3 minus U1 because this is right over here is U1 and this is U3. Okay, so U3 minus U1, so that is it for PAB, and this part is non-existent, so that is not going to be there. And cos theta, meaning cos 45 degrees, is 1, so there is no need to write multiplied by 1 here. So right after that we can move over to PAD cos 45 degree right over here. So PAD, here we have the EA by L 500, then we have UB minus UA, which is U7 minus U1. This is U7 at D joint, and at A joint we have U1, so U7 minus U1, then cos 45 degree because this angle is of 45 degrees. There we go, cos 45 degrees, and right after that we have U8 minus U2. So this is U8, the y direction displacement, and the y direction displacement for joint A. So this is U8 minus U2. Now this particular section of the equation is right over here, and at the end you can see that the whole part of PAD is now being multiplied by cos 45 degree because this cos 45 degree actually came in from here. So this is the cos 45 degrees right over there. Okay, So our equation is ready. So right after our equation is ready, we just need to simplify the equation, and then we need to move the unknown force into one side of the equation, right? So this is what is being done on the subsequent line. You can do multiple lines if you cannot do it at once. So the subsequent line is putting all of the values in the left hand side, while the value xa is being on the right hand side. Okay. All right. So similarly, you can do the same thing for FYA. And so the y direction equilibrium at A joint FYA. You can see that in the next slide. So we go FYA. You can do the same thing for FXB, then FYB, then FXC, then FYC, then FXD, and also FYD. So after doing all of this, we're going to get eight sets of equations. So these 8 sets of equations are the same equations that we had gotten from the stiffness matrix that we assembled earlier. So if we place the boundary conditions, meaning that u1, u2, u3, u4, and u6 are 0, and if we place this boundary condition in equations 5, 7, and 8, then we can solve for the displacements of u5, u7, and u8. And after that is solve the values of u5, u7, and u8 are gotten, then we can place those values in equation 1, 4, and 6 to get the support reaction forces. And once those are gotten as well, you can use the member force equation again to get the member forces as well. Okay, so this is how we can use the equilibrium of joints to get the same results that we have gotten from the stiffness matrix. This is something that we're not going to be using, but this is something that is possible, so it is shown here. Okay, that's it for this video. Thank you very much for watching.